Now called the Abacus Prize in 2010, and he got the Gödel Prize twice, and he also got the Breakthrough Prize in 2022. So please, Dan, the floor is yours.
Okay, thank you. I'll begin by apologizing. There was a typo in the title of my talk. The talk I advertised apparently was Discrepancy Theory is Mathematics. This sounds slightly more profound. I'll apologize. So briefly, what I'm going to tell you about is discrepancy theory. It's a mathematical theory that usually says if you give me a bunch of things like vectors, you can divide them into two sets that are very similar to each other. How similar? Well, at least much more similar than if you did it at random. That's our benchmark. And I'll tell you about algorithmic discrepancy theory, which takes these theorems and makes algorithms that realize their potential so we can use them and apply them. And then I'll tell you about my favorite application of this, which is in randomized controlled trials, where you have a bunch of subjects, you want to divide them into like a test group and a control group, and you want those groups to be similar. It seems like discrepancy theory is the right way to do that. So I will actually make the running theme through the talk be randomized controlled trials. We'll start with that, we'll end with that, and I'll use that to motivate discrepancy along the way. So let me tell you about how I learned there was something to be done to improve randomized controlled trials. My colleague Nicholas Christakis came and knocked on my door one day about 10 years ago. He was designing a study to test maternal health interventions. These are like village-wide social interventions to improve outcomes. They were testing this in rural villages in Honduras. He was concerned about the design of their study. Mind you, this is a huge study, $10 million, about a month before they're due to begin. He was concerned. So here's what was going on. They had 176 villages. I've plotted them in latitude and longitude. They're trying 16 different interventions. So they need to take these 176 villages, divide them into 16 groups. They're going to try something different in each group. That meant each group would have 11 villages, and I've given you a random assignment of villages to treatment groups here by color. So hopefully everyone can see at least some colors. And all the villages in the same color in the same group. Okay, here was the problem. This looks fine, but now let's look at the ones that are in light red. They're all in the western end of this region. And Nicholas had a concern. What if those villages do particularly well or particularly poorly in the study? Well, they'll be worried about whether it's something going on in the western end of the country. And even worse, will a referee be concerned that it was something going on in the country? And it's not the only bad example. If you look at the brown ones, they're sort of in this middle latitude. So what he was discovering is the law of small numbers. When you choose a small number of things at random, you see patterns, usually. So he asked me, can I help with this? And the problem was worse than this, or better, because again, this is a big study. They know a lot about these villages. They measured a lot of things about them. By the way, this was the day that I learned the word covariate as opposed to covariates. Covariate is the things you've measured about the subjects in your study. So they measured a lot of things they thought could affect maternal health outcomes, like altitude, income, all sorts of demographic information, distance to hospitals or how long it takes to get there when it's raining. I mean, they measured a lot and they wanted to balance all of these quantities. And I said, you know what? I can help you because I've been studying discrepancy theory. So now, so that you could help someone too, let me tell you a little bit about discrepancy theory and why I thought it was relevant. I'd like to start with one of the classic problems of by the way, just if you want to read some things, classics, like these are the books I look at, Chazelle and Matuszek in particular. There's some newer things in this panorama of discrepancy. And unfortunately, we need another book now. Maybe one is coming out. A lot of cool things have happened in the last decade that, well, a lot you'll hear about, but Okay, so here's one of the classic problems, like that Banaszczyk starts out with. He calls it Lebesgue discrepancy. I'm going to call it area because then I fit that word on my slide more easily. Here we want to approximate the unit square by a finite set of points. So I will find a set of points S. I'll call them x1 through xn the unit square. And our notion of approximation is that for every axis parallel rectangle, we want its area to be approximately the fraction of the points it contains. So for example, for this rectangle here, R, it contains 3 of the points. They're 25. So it contains 3/25 of the points in its area. It's about 1/8 of the square. That's a pretty good approximation. But we want this to be good for all of the rectangles. And the worst rectangle you can imagine is one somewhere down here. And that's going to be a pretty bad approximation. Okay, so we should ask, how good a set of points S can we find? Okay, one of your first instincts when you look at this should be to choose a regular grid. And this is okay. I will tell you now it's not the best. If you choose a regular grid of points and you take a half space that just like goes right above one of the rows, okay, if it's an odd grid, you'll get discrepancy like 1/2√n. We'll learn eventually you can do better. But okay, that's what a grid does. What about a random set of points? I told you that's what we're going to benchmark against. Honestly, the first set of points I showed you was random. Like literally, I generated this on the train yesterday with standard good pseudorandom generator. This is random. I know it looks like it avoids the bottom, but it's law of small numbers. Okay, but in general, if you're doing it at random and you take a look at, say, any fixed rectangle of measure a half, like the bottom half, just because of, standard deviations, you expect the discrepancy to be about 1/√2πn, similar to the grid. So we can't expect random to be that great. Okay, what can you do that's better? Well, I said this is a classic. Van der Korper, back in 1935, showed you can do better. He showed you can come up with a set of points where the discrepancy will be basically 4 times log n over n. And log n over n, that's much better than 1/√n. And that we now know is approximately optimal. By the way, the set of points I've shown you here is not Van der Korp's one. It's actually an easier one to describe. The way you describe it is you need a rational number, phi. And the set of points, for I from 1 to n, they'll be like I over n and phi times I. Mod 1, so just take the fractional part. The best rational number you can pick for this argument is actually the golden ratio, because it turns out that you get a bound on this discrepancy in terms of the coefficients that appear in the continued fraction expansion. And you want them all to be small, and golden ratio makes them all 1. So that's as good as you can do. Okay, this is like some of the classic results that you get from discrepancy. I'm going to talk about this. You can view this as not really dividing something in 2. This is really like approximating the continuum by a finite set. Sometimes we approximate a very big set by a very small finite set. But I want to tell you more about partitioning. This is called Tushnadi's problem for this variant of it. Here, imagine I don't care about the continuum. I have a different measure on the square. Maybe I just actually have a finite set of points x. So those are all of these points here. I'll call x. I want to divide that set into 2 parts. We'll call them A and B. So that for every single rectangle, the number of points of the rectangle in A is approximately the same as in B. So, okay, say for this rectangle, it had 4 points from B and 2 points from A. Okay, we'd like to see how well we can solve that. The best result that I know, although it wouldn't shock me if a better one had come out since, because there are people thinking about this a lot now, was Nikolov in 17 showed you can, for any set X, if it has n points, you can divide it into 2 sets where the difference would be at most the 3/2 power of log n. Probably it should be like log n or something, but we're at 3/2 right now, or best I know. Okay, once you can solve this problem, or you have good results of this problem, and by the way, as I said, like Banaszczyk called this the first problem, Lebesgue discrepancy, and of course you can consider shapes other than rectangles. There's a reduction from the partitioning problem to the general Lebesgue problem. So this is a good reason to just think about partitioning. If you can solve that, you can handle the other one. The reason is, well, what you do is you start out with a big set of points. Could be a big grid, big set of random points. But then if you have a good way of partitioning, you divide it in two. So here I, just whited out a bunch of the points. So you can divide it in two, and then just use 1/2. And repeat. So you take that half, this is just the half of the points that were left. I'm going to divide it in half again and just use these points that are blue. And if you keep iterating this procedure, the discrepancy that you get is really dominated by the quality of your partitioning. The initial big set of points and the discrepancy it had, as long as it's vaguely reasonable, sort of becomes irrelevant. So once you can solve these sort of partitioning problems well, you can solve the other sorts of flavors of discrepancy problems. Partitioning ones are usually more difficult. Okay, so I said I'm going to usually focus on the partitioning problems, but let me just mention a few good things about area discrepancy and their relations, because it's related to a lot of things. First one is Monte Carlo integration. Like if you have a very complicated function that you want to integrate, Monte Carlo integration says, well, you know what? Let's just evaluate at random points and take the average and see how quickly it converges. Well, if you want to converge more quickly than random points, you might choose your points carefully. That gets you to quasi-Monte Carlo integration. And discrepancy has been used for that. There were some recent improvements in that by Bonsall and Zhang, who improved it, again, going through the partitioning approach to even just the standard Lebesgue problem. You get better bounds for it. It's related to a fundamental problem in statistics, which is called survey sample. That's when, well, imagine you have a lot of people and you want to send surveys to a few of them. Or you're picking a small number of individuals to study or measure. And you want them to be representative of the whole. So you have to know things about them so that you can make these choices. But how you make those choices is related to survey sampling. That's related to this area discrepancy. I'm also, especially for those who know me, graph sparsification, where you have a graph with a lot of edges, you want to approximate it by a graph with a few edges, is really an example of this. And the partitioning problems are harder. Okay, so that is a sort of discrepancy theory that's very good for low-dimensional problems. 2 dimensions, 3 dimensions, 10 dimensions gets really rough. Everything is going to scale with the power of at least the dimension. Okay, so here's another discrepancy problem that makes sense in higher dimensions. I'm going to call it Euclidean discrepancy. Maybe someone will tell me it has a better name. So let's say I have a bunch of vectors in d dimensions. Think of it, n vectors, d dimensions. Think of n as being comparable to d, if you like. They can be on the same order. But they should all be bounded in norms. Let's say they all have norm at most 1. I want to look at dividing them into 2 groups. So I'm going to take one group and subtract the other. So imagine I'm assigning plus or minus 1 signs to each of these vectors. And I'm going to look at the sign sum. I'll call it S. So z of I will be a plus or minus 1. Okay, we can ask how small can this sign sum be in norm? A simple result is what happens if you choose the signs at random. And if you choose the signs at random, it's not hard to show that, well, the expected squared norm of the sum will be at most n. So the norm we should expect root n. Actually, I'll prove that for you in a minute. Can you do better? Well, there are some results. If you combine papers of Brown and Grinberg and Beck and Fiala from 81, you can show that there do exist signs so that the norm of the sign sum is at most root d. Okay, so I said let d be comparable to n. Imagine d is a little smaller than n. This is interesting. Actually, if d is a lot smaller than n, this is even more interesting. So you can always find a sign sum where this is small. And this result, there's an algorithm for, and it's tight. Okay, so you give me any set of vectors of unit norm, we can find a sum of them, which is going to have small norm. I'm going to tell you roughly how we prove that, because it's a very useful first step. And this proof is the template for many things that have followed. Oh yeah, and just here is my sort of picture. Like I've got these vectors, got to assign them plus or minus 1 signs, and I want the sum to be small. So the way you prove this is first, let's think about the case where n is equal to d. And let's look at what happens with random signs. And we can just compute what the expected norm squared will be. So if z's i's are random plus or minus 1 vectors, I want the expectation of the squared norm. First, I'm going to expand the quadratic using this notation for inner products. So you expand the quadratic into sum over all pairs. Then you just say, okay, expectation is linear. So we reverse the summation in the expectation. Now we have a sum over all pairs of the expectation of z of I, z of j times the inner product of those vectors. But if z of I and z of j are independent plus minus 1 signs, that expectation is 0 unless I is equal to j. Okay, so because z of I times z of j is 0, expectation 0 unless I is equal to j, we only sum over the terms where I is equal to j. And then we're summing the, well, that's just now since I is equal to j, that's the squared norm of xi. We're just summing the squared norms of the xi's.
Sorry, I have a question.
Yes, please.
You, ask for not maximum discrepancy, but average discrepancy typically, then random is best, right?
Ooh, that's a good question. I don't know if random is best. And I will admit, yesterday on the train, I was like looking through a section of Matuszek's book on average discrepancy, but I didn't look at it carefully enough to remember the results.
Okay.
It could be. It's a good guess. Okay, so now that's what happens when n is equal to d. But I said this theorem is more interesting when d is much smaller. We're going to get root d instead of root n. So how do we do transfer from one to the other? Well, here's sort of the argument. It is going to reduce the n is equal to d case. The first step is you follow this procedure in this paper of Beck and Fiala. What it will do is it will produce a vector called z hat that's not quite plus or minus 1. All the entries are between minus 1 and 1, and many of them are plus or minus 1. How many? N minus d of them. So you're only off on d. All the rest are plus or minus 1. But it also has this property that x times z hat is 0. Oh, did I say x? Right, x, I'm just taking the xi's and putting them in the columns of a matrix. So that's now my sign sum. X times z hat is my sign sum. The sign sum is 0. So we have a lot of things that are discrete, a few that are real valued. And then what you do is you choose z by doing what's called randomized rounding. That means any entry of z hat that was 1, you keep 1. If it was minus 1, you keep minus 1. Everything else, you make 1 with probability proportional, but how close it was to 1. So things that are close to 1 are more likely to wind up at 1. And then if you analyze this, just use the same analysis I gave before, you wind up seeing that the expected squared norm of xz is at most d. Because there were only d terms, and it's usually better. That's like if z hat had d entries that were 0. You're even a little better if bunch are already close to 1 or minus 1. But the key point is the plus and minus 1 values don't change. Okay, so the question is, how do we get this vector z hat? So xz is equal to 0, and that's d linear constraints, but most of the entries are plus minus 1. Okay, I realized I wrote an algebraic proof. Let me give a picture proof.
Just because of linearity?
It's just because, okay, yeah, it's like, you can do it by dimension counting, linear programming duality, but I want to do it a dumber way. Sorry, a slower way that's actually going to be very useful. Okay, so let me give you the dimension counting version. So here's our hypercube. And if imagine x is d is equal to 2, and I have 3 variables. So if I take a look at the plane, xz is equal to 0, if it has dimension 2 and you intersect it with a hypercube, you expect it to hit at a face of codimension d, which means that actually n minus d of the constraints are quite, so you have n minus d plus or minus 1s. Okay, so that's an argument that tells you there's a solution. In fact, there are many solutions. I mean, here I drew 4, there are usually going to be many. Okay, let me make this a little more algorithmic. I say it's not as smart a proof, but it's going to turn out to be very useful because it's more flexible. So the way Beck and Fial did this, said, let's imagine an iterative process where I start out at the 0 vector. It's in this plane. Now pick a direction, any direction in that plane, like this one, and just move in that direction until you hit a face of the cube. As soon as you hit a face of the cube, some variable has been set to 1 or -1. And now you can say, okay, can I move again? Well, you count dimensions. You have a number of constraints, which is, okay, sorry, say once I'm in a face, I want to stay there. Once I got a vector that's 1 or -1, I want to keep it there. Okay, so you have a constraint. Any variable that you've set to 1 or -1, you want to keep 1 or -1. And you have a constraint, you want to walk inside this plane. But as long as the number of constraints is less than n, there is a direction you can walk and move. So they'll say, okay, we walk from here in this plane, I wind up hitting this face, that's this edge, at that point I'm stuck. That's what Beck and Fial did, and then they do this random rounding. And that will take me to this corner with higher probability than that one. Okay, the reason I like this algorithmic proof, where you take these steps, is that people have made a lot of progress proving theorems in discrepancy theory by observing, that there were actually many solutions I could have gotten to here. And if you're very careful about which direction you step, you can get to solutions that are better and have other nice properties or solve other discrepancy problems. And I'll mention some of the other ideas for how you take these steps. But actually, a huge amount of thought has gone into, you give me a discrepancy problem. How do I think about like what are the right directions to step and how do I prove they exist and things like that. Okay. Oh, by the way, I should have mentioned at the bottom, so this has been used, a process almost exactly like this in a paper of DeVille and Thiel for survey sampling. They were figuring out which towns in France and some parts of Spain to include in census surveys. And they invented an algorithm that does this sort of process. Here they use an integer linear program instead of randomized rounding. They didn't know anything about Beck and Fiala. It was completely independent. It's called the cube algorithm. And that's what people in survey sampling know. Okay, but you can ask yourself the question, is getting similar sums sufficient for like the problem Nicholas was asking me? So here's an example of some points where you should think it's not. I made these 8 points and I divided them into 2 groups. And well, here I drew the centers of the groups, almost exactly on top of each other, the means. So I mean, sums are going to be similar. But these 2 groups do not look like each other. Like these sums are almost exactly in this line, and this group is almost exactly in that line. And if you rotate this 45 degrees, you're staring at exactly the problem that Nicholas was unhappy about with his villages. So, okay, maybe you want more than sums to be similar. What can we ask for? Well, a thing you can notice about these points is that while their sums are similar, their second moments are very different. The moment ellipses of these points goes this way, and the moment ellipses of those points goes this way. Can you divide them into 2 sets so that the moment ellipses will be similar? Well, let's measure those more concretely. So here would be the division, by the way, into 2 sets, and I drew a cartoon of their moment ellipses. So give me any unit vector u. The moment in direction u is just the sum of the squares of the inner products of u, the xi's. So now here's a discrepancy problem. Can I pick signs, say z and plus or minus 1, so that when I sum the signs of these, so okay, or take all the ones in the positive group minus ones in the negative group, the difference is small. Say most sum epsilon. Can we make the moment ellipsis close? Well, we can. This was Weaver's discrepancy problem. So the way which Marcus Srivastava and I solved. So the way Weaver's discrepancy problem is set up is first, let's normalize so the moment ellipses of all the points is just the sphere. Do a change of variables so the sum of the outer products of the xi's is the identity. Okay, then in order to make this problem solvable, there need to be no outliers. Like there can't be any point that is, say, orthogonal to all of the others, because then that point you'd want to have in both groups. That's not okay. Okay, if there are no outliers, which we'll describe here, given that condition, it's sufficient to just put an upper bound on the norm of the xi's. Then there is a division of the points into two groups, or assigned plus or minus one signs each, and so that all of the difference in the moments is at most 6 times alpha. You can get a slightly better constant, but this is good enough. Okay, so we weren't thinking about randomized control trials when we worked on that. We were thinking about discrepancy theory, and the reason we were is Nick Weaver's posed this problem in discrepancy theory as a way to get people who think about discrepancy to work on Caddis and Singer. And it's a very nice connection he made, because then we could think about that problem. Okay, so I knew how to do this. But here's some issues that get in the way of using this for Nicholas's problem. The first one is, this is an existence result. I mean, this proof is about real stable polynomials and roots of polynomials. That doesn't have an algorithm. We still don't have any idea if we can realize this algorithmically. Second, I've sort of blurred something. We don't know how to simultaneously get this guarantee and the guarantee that the means are similar. I mean, boy, we should, but they're very different proof techniques and we don't know how to combine them. So that's a nice open problem for someone. Okay, but on the other hand, I spent a lot of time working on this problem. I had a lot of code that, usually works. So we ran that. And I gave Nicholas this assignment, and you can't quite tell, but it villages and groups of balances, all of his core, every measure he had very well. The each group, the latitude and longitude, all of their covariates were balanced too. And I said, okay, here you go, you can run your study. And then Nicholas sort of said, but how do I know this isn't somehow bad? I was like, why are you asking? It's like, my algorithm doesn't know anything about your problem or your data. How could it be bad? And I was upset. But after some conversation, I realized he had a legitimate concern. There's a reason the word random is in randomized controlled trials. He needs to be able to argue in the end of the day that it is actually unlikely that the results are due to a poor assignment. And if his assignment is Dan ran this algorithm, then there's no way to make that formal. You need randomization to do things like make confidence intervals. If you want to complete p-values, it doesn't make sense without randomization. Also, I'll add, you can do things better on average and balance, yes, than you can in the worst case. So coming up with a random assignment gives you a lot of power. So here's what I learned. His problem, well, he told it to me and I said, this is like an optimization problem or discrepancy theory. It wasn't really an optimization problem. Really, they want a distribution on balanced partitions. Okay, you could now pick it an optimization problem. It should be the optimal distribution on balanced partitions. And we can define what that means. I'll hint at it later. But that's what they needed. So let's take a look at where we are now and what are the obstacles to helping us. First, especially if you want to make a general theory, not just help your friend, but actually write a paper and write things people can use. We need efficient algorithms that have guarantees. Like if someone's going to spend the time to run your algorithm, you want to be able to promise them that yes, it will do something good. And you need to analyze it. So we can't just run my heuristics. We need to get a distribution on solutions, not just one. And it's what's nice is I'm going to tell you a way of doing that, and it's going to avoid the need to solve the Caddis and Singer problem in any instance. I mean, I would like to be able to have algorithms for it, but since I can't or don't know them yet, get the distributional thing is going to be really good. Also, of course, we need to formalize what is the statistical problem we're really trying to solve. It's not enough just say these two groups look similar. Like you need to think, what does that mean for the statistics you're going to compute? I'll only tell you a little bit about that. I want to tell you more about the advances in discrepancy theory that we leveraged. So to do that, let me tell you about one of the other classic problems in discrepancy theory that's motivated a lot of work. I call it Spencer's problem. So let's say we're trying to run trivia night at the School of Mathematics, and we need to divide people into 2 teams. So we do a little survey of these people. Here I have 8 people. You can ask, like, are you a mathematician? Are you a computer scientist? And we're going to balance the teams on that. Are you a student? Okay, here are not many students. But what editor do you use for writing your math? And now we want to divide people into 2 groups that have different, the backgrounds are balanced. So let's add a column here, which is going to be like group tells me who's in group A and who's in group B. And then I want to make sure that there's small differences in totals between the groups. So I will compute the sum over group A of these quantities, the sum over group B, and then look at the difference, that vector. And what Spencer asked is, can we make the infinity norm of that vector small? Okay, so one thing I will mention is to go from the Euclidean problem I described to this Spencer problem, we're changing from 2 norms to infinity norms. I'm really having a vector for each row here, and it has an upper bound on its infinity norm. Well, the answers are 1 or 0. And here I'm asking for a bound on the infinity norm as my guarantee. Ask, how well can you do that? Well, and if you want to do this asymptotically, let's say we have n people in D covariates. You can ask, what happens if you do it at random? That's our benchmark. We want to beat that. Okay, if you do it at random, you should expect the infinity norm of the difference to be up to a constant around root n times log d. The reason there's a root n is if I do it at random, in each column, the standard deviation is going to be root n. And you might not see that, but if you have d columns, you probably see that. And probably one of them is actually at least root log d, if you have d columns, times the standard deviation. So random will get you about root n times log d. Spencer proved you can do much better. There's this beautiful paper called 6 Standard Deviations Suffice. And he proved that actually you can divide them into 2 groups. So the difference is at most 6 times root d. Okay, now if d is less than n, this looks sort of amazing because root d would be much less than root n. That's actually not what people were excited about. Because from the previous Beck and Fiala procedure, we sort of know how to reduce the d to n. And again, roughly, it's like this change of norm from Euclidean to infinity norm, but that basic procedure works. What drove people crazy was the fact that this was a 6 and there was nothing logarithmic there. Actually, it wasn't even a 6. He called it 6 standard deviations because that sounds so nice. It was actually like 5.32. But who wants to read that in the title? There was nothing logarithmic here. And it was not clear to anyone that you should be able to avoid a log in this, especially in any sort of theorem. But you got a constant. I should also mention, like 6 root 5.32 doesn't really beat out like a root log d when d is small. But when d is small, also, it's not 5.32. It could be smaller. Yeah, analysis is for large numbers. Okay, but when Spencer proved this, it didn't have an algorithm. This is an existence result. It uses probabilistic combinatorics, but there was no obvious way to try to come up with any efficient algorithm that would match these guarantees. And early on, like just a few years after that, people started conjecturing maybe there is no polynomial time algorithm for this. Maybe this is one of these things we know exists, but you can't find. And after 20 years, I think a lot of people were pretty sure about that. Until in 2010, Nikhil Bansal came up with a polynomial time algorithm for realizing the guarantees of Spencer's problem. And I mean, this is more than just an algorithm for Spencer's problem. It is a sort of paradigm for how to solve discrepancy problems. It's different, and it's a different way of thinking about them. So since this algorithm, we have solved many, many more discrepancy problems, sort of by roughly, and I'll show you some pictures, is taking those steps in that hypercube intersected with the plane intelligently. And come up with algorithms, proved a lot of theorems. I will mention, I'm still really curious about the right constant for Spencer's problem. When n is large, the best lower bound we know is 1 from a Hadamard matrix, and the best upper bound we know is like 3.67 from a paper of Byzantine clouded. I'm suspecting 2, but I really love proof or disproof. So let me know if someone finds that. Okay, so rather than telling you exactly how Bonsal's algorithm works, let me tell you how Lovett and Mecca's algorithm, simplification of Bonsal's algorithm works. There were many papers published coming up with other ways of realizing Bonsal's ideas. So here was their idea. So first, I'm going to cheat. I'll solve a slightly simpler problem. I want to find a vector z in the hypercube. So all entries between 1 and -1. I just want most of the entries plus or minus 1. And then I want small discrepancy. I'll measure that by the infinity norm of xz, the infinity. And I want that to be most c root n, so that will be right. But I'm not going to get all the entries plus or minus 1. There's a procedure you can clean up recursively to fix the rest of the entries. Okay, what they suggest doing is following Brownian motion. Okay, they're going to discretize it because we want an algorithm, but let's ignore that for now. You start at the origin and you look at this polytope, which is the hypercube intersected with the vector z of low discrepancy. We do Brownian motion here. We call it sticky and Brownian motion. Once it hits a face, it stays in that face, and then it keeps walking. Eventually, it hits a corner. So let me draw that more slowly. Here's the hypercube. Here's the hypercube intersected with the vectors of low discrepancy. They're both polytopes. And you'll notice like I drew it just sort of cutting off some corners because this is a much bigger polytope than that one. I'll define that precisely in a moment. Okay, so here's the idea. You do Brownian motion, starting from the origin, you eventually hit a face. Once you're in that face, you stay in that face, and then you do Brownian motion there. Walk around till you hit another face like this one. And okay, it keeps walking, it eventually hits a corner, which will be, say, this one. And then you take a look, okay, it has 2 coordinates that came from the hypercube, so 2 coordinates wound up being plus or minus 1. We're sort of happy with that. Okay, so I should tell you, oh, here I wrote it stops when it's a corner. What do I mean when I say that this polytope of vectors of low discrepancy is much bigger? You got to think about how you're going to measure volume. The way they measure volume is by Gaussian measure. So this is, you can write it as an integral, but it's the probability that a Gaussian random vector, variance 1, centered at the origin, lands inside the polytope. If you take the hypercube, its Gaussian measure is pretty small. It goes exponentially small in n. Just because, you know, the unit interval from -1 to 1 is a constant, and then you take the constant Gaussian measure about this, and you take the product of n of those. This polytope, on the other hand, has Gaussian measure close to 1. So it is a much bigger polytope. And that, roughly speaking, is why when you do all of this Brownian motion, you are more likely to hit faces of the hypercube than you are to hit faces of this low discrepancy polytope. It's very hand-wavy, but it was an important idea. Also, it takes this idea of Beck and Fiala, which I was saying, take steps to all the way to the side to taking smaller steps. I should also add, it is now the 3rd reason that my graduate students have to learn about stochastic differential equations. The second one being stochastic localization, and the first being generative AI. Okay, so let me tell you a little bit where things went and leverage a little more convex geometry. So we now sort of have this idea that I can characterize different discrepancy problems by thinking about different norms. The Spencer problem said, okay, assume my vectors have an infinity norm at most 1. I'll try to get an upper bound on the infinity norm out. This Euclidean problem worked with Euclidean norms. Cohn-Losch's conjecture tries to get the best of both of these. We don't know how to solve this yet or prove it, or if it's even true. Cohn-Losch's conjecture says that if all the vectors have Euclidean norm at most 1, then there is a signed sum where the infinity norm will come out at most a constant. Okay, and I know it's not immediately obvious, but this does imply both of those. The reason is the root D's appear when you change from infinity norm to norm. Okay, we'd really like to know if that's true. The best lower bound we have is due to Tim Kuniski, who got a 1 plus root 2. For a long time, the best result we had on this was due to a theorem of Banaszczyk. So Banaszczyk considered a case where you have Euclidean norms on the input vectors, and we're trying to get a norm defined in terms of a convex body on the alpha. Let me explain what that is because it's proved very useful. So Banaszczyk's theorem says, let's say I give you a bunch of vectors of norm at most 1, and I give you a convex body. It's got to be sort of big. So by sort of big, I mean it has to have Gaussian measure at least a half. And then it says, okay, if you have that, then there is a signed sum of the input vectors. I'd like to put them in the convex body. I can't, but I can put them in 5 times the convex body. Okay, the reason for Gaussian measure a half is that's enough to guarantee that you contain the origin. And the problem is pretty clearly not solvable if you don't contain the origin. Like if I don't contain the origin, then there's a half space and separating this, and I can take vectors orthogonal to the boundary, and every sum of them won't land it. Okay, so this is a theorem. Oh, by the way, in this theorem of Banaszczyk's also generalizes some of the things we know. For example, the Euclidean case. So if you think about the Euclidean case, you're trying to get 2 norm at most root D. If you take a look at the ball of dimension root D in D dimensions, that has Gaussian measure about a half. So Banaszczyk's theorem generalizes, but here's the thing. Banaszczyk's theorem is a theorem in convex geometry. It's an existence proof. It did not come with an algorithm. It was not clear at all if you could do this. But I say, it doesn't get you Cauchy conjecture. It gets you the best thing we had. The constant C you get to where it works is about root log n. Sorry, I'm not going to describe this slide enough, but it was the best we had for a long time towards Cauchy's conjecture. Okay, so people were trying to come up with an efficient algorithm that would realize the guarantees of Banaszczyk's theorem. And there was this really remarkable paper of Nadoush, Garg, Lovett, and Nikolov, which observed that Banaszczyk's theorem is equivalent to the following remarkable statement. So that if you give me any input vectors, x1 through xn of norm or most 1, there's at least a distribution on random plus minus 1 assignments, okay, distributions I'm going to want, so that the signed sum is a sub-Gaussian random vector for some constant variance. Okay, I realize maybe not everyone knows what a sub-Gaussian random vector is. Just think concentrated at least as much as a Gaussian will work for now. There are actually many definitions that are equivalent to each other. Okay, so it said that if you can get, the other thing about it is they were doing this to say if we can make this distribution, if I can find such a distribution, then I've got another proof of Banaszczyk's theorem. Yes?
Can you repeat what was sigma?
Oh, so, okay. So actually, I didn't tell you, it should be a constant. All they care about is a constant. The constant affects the 5 in Banaszczyk. Okay, so it's a spoiler. In their paper is root 40, in my paper it's 1. So we do know the optimal constants. But, okay, so but what, by the way, the proof of this is not terrible. I mean, it's actually conceptually very clean. It's sort of like one direction about sub-Gaussian measures uses this theorem of Talleyrand on majorizing measures. You know, these things are about sub-Gaussian measures. And the other direction is really von Neumann's minimax theorem. So it's a clean thing. But then Dadouche, Bonsall, Dadouche, Garg, and Lovett came up with a polynomial time algorithm that samples from such a distribution. And that got us a polynomial time algorithm for Banaszczyk's discrepancy problem. So literally, their algorithm takes some input vectors, comes up with a random signed sum of them so that the sum is sub-Gaussian. Oh, wait, I think my next slide specifies it precisely. Yes. So, okay, so they have a polynomial time algorithm that on input any vectors of norm, each is norm-most 1, chooses a random z but not uniform, like a very carefully constructed distribution. So they don't construct the distribution, they construct an algorithm that samples from the distribution. And the result they proved is root 40 sub Gaussian. And they weren't caring about constants. That's enough to get Banaszczyk up to a constant. Okay, I feel like, right. One thing I should emphasize, which is sort of cool. This theorem doesn't actually know about the convex body you're trying to prove the point is contained in. It just, once you have this sub-Gaussian property, you're good. Sort of Talleyrand's theorem then tells you, okay, you're in that convex body with some constant probability because it had big Gaussian measure. And Talleyrand proves sub-Gaussian random variables for discrepancy sort of problems like this, or containment in a big convex body, are sort of the same as Gaussian ones. I'm not going to tell you about the proof. I unfortunately cut that out, but I will say it follows this sort of procedure of Beck and Fiala of taking steps in a hypercube that I mentioned before. It's not small steps, it's big steps, but the directions are very carefully chosen by a procedure that looks a lot like a Gram-Schmidt orthogonalization, but not exactly that. It's a very remarkable algorithm. Like when you read it, you say, why does this algorithm work? And then once you understand it, you realize you had no choice. This was the algorithm. Okay, for my own purposes, where I want to apply this, root 40 was not very good for me. So Chris Harshaw, Frederick Savier, Peng Zheng, and I spent a while working on this, and we got the constant down to 1. I will admit, the way we started out was just trying to come up with other algorithms for the problem, because they have their algorithm, they had a root 40, and we figured, okay, and we need another algorithm. And Pong has a cool paper on some other simple algorithms that get you the right things up to a constant. But we know some other algorithms for this, but it turns out their algorithm is the right one. Like that's the only one we can prove a constant 1 for. That did require a bunch of reanalysis.
I assume you've implemented it.
Yeah, oh yes, it was implemented. Right now, we wouldn't have guessed the constant was 1 if we hadn't implemented. I mean, I was literally on a plane flight implementing this thing. And when I got off the plane, I sent an email to them. It's like, it looks like this thing gets 1. Who knows? Okay, so now I can tell you how we can formalize. I'm sorry, I'm going to do this only in 2 slides, but how we can formalize what people want out of this sort of thing when they're designing randomized controlled trials. So first, one of the dominant ways people study randomized controlled trials or experiments or things, it's called the Neyman-Rubin model of experiments. Let's just consider partitioning subjects into 2 groups, a test group A and a control group B. They imagine that there are some potential outcomes, meaning if subject I is assigned to group A, we say their outcome could be little a of I. Subject I is assigned to group B, their subject is little b of I. Those could be things like Boolean variables, like did that person get the flu in our experiment? Did we assign them a mask or not? It could be number of years they lived after taking a medication or something like that. But we don't know these a of I and b of I's. We're trying to figure out, like, is group A better than group B? So what we want to do is we want to estimate what's called the average treatment effect. That's the average of little a of I minus little b of I. And the reason this problem is hard, well, there are 2 reasons. One, we're making really no assumptions about what these things are. 2, you never get to observe both little a of I and little b of I. Like you can't have masked on your way to this conference and not masked on your way to this conference, right? We don't get to observe both. So what you do is you estimate this. And I'm going to suggest using what's called the Horvitz-Thompson estimator, but it's the simplest thing you can imagine, or second simplest. Sum the AIs in group A and subtract off the BIs in group B. Use the data you got, right? And then we're just going to scale it by 2 over n. That scaling has the very nice property that our estimator is right in expectation. So the expectation of the estimator does agree with what we're trying to estimate. Okay, but now expectations, you got to worry about the error. What's the chance it's far away? So what you do is I'm going to measure for you the mean squared error. And I'll tell you what we do is, okay, I didn't mention, we also assume we have covariance, meaning there are things we know about our subjects. That's what makes us all relevant. If I don't know anything about the subjects, just divide them up at random. If I do know things, we're going to feed those, we augment them in a way, and we feed them into this Gram-Schmidt-Walk algorithm. Okay, and we get an upper bound on the mean squared error. And well, before I tell you about the formula, let me tell you about the guarantees. First, I can answer Nicholas's question of could this have been bad? We can say, no, it can't be much worse, or can't really be worse than what you wanted to do, which is what you wanted, or your initial instinct is divide at random. Okay, that's why I wanted that constant 1. If it wasn't 1, it would have been root 40, and I said this can't be more than root 40 worse than dividing at random. In which case, you would have never talked to me again. You need 1. Okay? But also, if the covariates actually correlate with the outcomes, if they're predictive, at least linearly, then you get smaller confidence intervals. Then you have lower mean squared error. So the way the mean squared error is written is basically you minimize over some parameters beta. You're going to take their inner product with the covariates. And you pay something for having a large beta, but otherwise you subtract that off from the sum of the covariates. If you stare at this formula, you might recognize it as what's called a ridge regression. It's literally measuring how much is the sum of the potential outcomes correlated with a linear function of the covariates. So the smaller that is, the better you do. But here's the thing. Again, I told you I'm using this Horvitz-Thompson estimator. All I'm doing is I'm summing the data that I've got. There is no regression I'm suggesting performing. We're always nervous about that because if you actually do a regression and you have things you haven't observed, we don't quite have a good theory yet for what the error of that will be. People are working on that really hard right now, like papers every month, 6 months, let's say. Okay, but this is an artifact of the design. That is, this is an artifact of using the Gram-Schmidt-Walk, balancing covariates. What does balancing covariates get you? It gets you that taking the sum of the data you get, or the difference, actually bakes in a regression, which I know sounds totally counterintuitive, and I don't have time to prove it for you, but I will tell you how to get to that intuition. Many of you will have an intuition that if you want to do a randomized trial, you should have your test and control group of the same size. And if you try to make that intuition formal and figure out what it gets in mean squared error from an estimator, if you just take this estimator, it tells you that essentially you're masking out the means of the data. So, okay, if you try to justify making two groups of the same size and you go through the math, it gets you something similar. But we're just not dealing with the means, we're dealing with taking out the effects of the covariance. Okay, if you want to find out more, I recommend either a paper, which was in JAZA. They have a page limit, so I honestly really recommend the archive versions where we have much, much more, and many more results and experiments and things like that. Okay, good. I made it to the part I wanted. Tell me about some recent developments in open problems, which means I clearly had too much coffee, but I made it this far. Hopefully you had coffee too. Okay, so we were talking about discrepancy by norm and measuring different norms. I mentioned the Komloff conjecture and Banaszczyk's theorem, which was a result towards it. There has recently been a result a few months ago of Bonsall and Zhang that gets us much closer to Banaszczyk. So into Komloff, previously we had a constant here, with Komloff suggested to be a constant. I said order of root log n. They got it basically to the 1/4 power of log n. So order log n to the 1/4. Okay, to me that suggests this should probably be a constant. Like I just can't believe that log n to the 4th is the right solution to almost anything. But who knows? The argument goes by taking much more careful steps inside the intersection of these two polytopes, roughly. Some cool ideas. I will mention another one, which is you can also look not at normal vector norms. You can look at, and this sort of we suggested earlier, you can look at matrix norms. That's what we're talking about when we look at are moment ellipses similar. So one way of understanding this theorem of Marcus-Srivastava in mind is we say we have some vectors of norm at most alpha, and their sum is the identity. You can talk about the sum of the sine sum of their outer products. That's what we were doing when we were looking at the difference in moment ellipses, and we said that, okay, the operator norm of that is at most alpha. When you look at this theorem, it's very natural to say, once you phrase it this way, why am I restricting myself to rank 1 matrices? Why not consider general matrices? And that was done by the natural analog then. Instead of taking a look at the norm of those matrices, and natural ideas look at their trace. So Michael Cohen and Peter Brandon independently came up with proofs that say if all the matrices are bound to trace and their sum is the identity, then we can come up with a sine sum. So that the 2-to-2 operator norm is bounded. There's a big conjecture in this area called the matrix-Spencer conjecture. It's a matrix version of Spencer. Our first time, it's what you get if you take matrices where you put Spencer's vectors on the diagonal. But now instead of taking a look at the largest entry, we look at an operator norm. The conjecture is if I give you a bunch of matrices with operator norm at most 1, there should be a signed sum of them where the operator norm is at most a constant times root n. You can't hope for better than that. There has been a lot of progress on this. Well, a lot. An exciting one from a few years ago of Bansal, Zhang, and Mecca proves this is true as long as the rank of all the matrices is bounded. It needs the rank to be at most n over the log cubed of n. And their paper is remarkably simple because it gets to draw on a more complicated paper of Bandiera, Bodhihara, and Van Handel, which improves some theorems in random matrix theory. Roughly speaking, like Spencer's case of this theorem is the diagonal case. In that case, well, we know Spencer's proof. When the matrices sort of very strongly don't commute, this becomes something that you think of as being free probability. And that's what that other paper leverages better random matrix theory for. So sort of we're in this case where sort of things very much commute. We have Spencer's theorem, but if they very much don't commute, we have some others. And in between, okay, it's not beautiful yet, but maybe someone will make it better. Part of the issue is defining what it means to not commute. Like Trop had a definition that got some improvements, and then there's some better things, but, or, we don't want the definition not commute. We need to measure how much, and it's not just 2 matrices, it's an ensemble of many matrices don't commute. If there's just 2 matrices, I think we got the measures. Okay, every time you show a computer scientist a problem, they'll say, what about the online case? What that means is, what about when your data comes in over time? Like in randomized trials, think about most medical trials. Like someone comes into the trial, and you need to decide that day, do you give them the vaccine or a placebo or something like that? You can't gather all of the subjects often and then decide what to do. In public policy interventions, where you're like testing interventions in high schools or villages, yes, you measure everything in advance, you know who your subjects are, and then you run the trial. Okay, so we want to solve these problems in the online version. Discrepancy. So there's this very cool paper of Lusa and Simonyi says we can almost do that. Like, okay, there's a root 2. Simonyi told me it's a little better than root 2. It's a Gaussian guarantee. You can get in the online version of that vector problem, but they have to discard some fraction of the subjects, about 5%, which maybe that's okay. But and I'm not going to get to how it works, but that still. But I may be able to say you can do something without discarding subjects. There's a theorem of Kulkarni-Rees and Rothfuss that says you can get a root 10 Gaussian guarantee, not as good as root 2. Don't discard any subjects. So they can do online what this Graham-Schmidt-Walker algorithm does, but let me say it's a little bit better than existence result, but not exactly. Like it is a doubly exponential time algorithm. So 2 to the 2 to the n, where n is your number of subjects. You're not going to run that so easily. Okay, so the big open problem, which I conjecture is, I do believe you should be able to get 1 sub-Gaussian online by an efficient algorithm. I don't know how to prove it yet. I've been banging my head against that for around 5 years now. So, you can stop the banging if you can. Good way to do it. I appreciate it. On that note, let's get in line.
Thank you, Dan, for a great talk. We have open for questions or comments. Yes.
I'm curious if you could say something about in a world where this sort of non-random sampling became more common, how you would run like meta-analyses, because it seems like you're saying that smaller studies would now be more powerful, but we don't know exactly how much more powerful. So how do you tell the difference between people publishing, publication bias versus studies that are more powerful than you realize?
It's a really good question. Okay, so I have ideas. I don't have the perfect answer. So one other thing what inspired my ideas is we're not the first people to balance covariates, right? There's a lot of people who said, let's try to make covariates similar in test and control groups. And there are many papers on this. Just they don't oddly tend to come with formal guarantees. And I actually think it makes a lot of sense to the extent that people published procedures that you can understand and they made them formal. You can then go back and analyze what were the sort of guarantees you should be able to get from that. So this actually gets into some very current topics in theoretical computer science and statistics. I suggest I like the sub-Gaussian property. So this means that if you gave me a covariate balancing algorithm, you should be able to then look at the procedure specified in a paper and ideally then figure out produce things that are sub-Gaussian. Sub-Gaussian gets you to things like central limit theorems. Maybe you don't want as much of that. Maybe you want bounded moments. And okay, so this gets to what some people call property testing, or the questions people study. If I give you samples from a distribution, can you tell, does it agree with something like a sub-Gaussian distribution or a distribution of bounded fourth moments or things like that? There have been recent papers on that using sum of squares and things like that. So that's at least a direction towards an answer, I hope. Otherwise, you do hope that people have specified their procedures carefully. I mean, by the way, like some of the crudest covariate balancing will be aggravating. Like if you look at the COVID studies like that Pfizer did, they did a little bit. They divided people into 3 groups. Those, I think it was 65 and older, younger than 65 with pre-existing conditions, or just everybody else. And then they did choose an equal number of people in each of those 3 groups, or in both groups. But when you're recruiting 10,000 people, it feels really silly to only be balancing like 1.5 covariates. Really, we should be able to do much more, but I'll admit, I don't have the theorem for it yet. So, yeah.
Do you have any examples in mind where doing what you did at first, of just running your optimized discrepancy algorithm instead of choosing distribution is actually a bad idea?
Oh, it's a good question. Do I know it's a bad idea? No, I can never know it's a bad idea. Like to do something, because I don't know all of these unobserved potential outcomes.
Like, is there an example where there is some unobserved?
So you're getting into a very dicey issue in causal inference, and this is why there's some controversies in the field. It's because we don't have great benchmark data, unlike, say, that's motivated most of machine learning, because you never observe these things that are unobserved. People come up with synthetic data. And yeah, then you can cook up examples where doing something deterministic will be bad. In some sense, if you give me any deterministic procedure, I can make something where it will be bad. Or come up with potential outcomes where it will be bad and they won't look crazy. Okay, maybe that's a good answer. There are other covariate balancing procedures where it's sort of easier to break them. Like things people often hear about is matching. You take subjects divide them into pairs that are similar and like flip a coin for heads or tails. And that's fine in 2 dimensions if you only have 2 covariates. But if you have many covariates, it doesn't. It has big problems and it's pretty easy to show. Actually, there you don't even need to make adversarial data, just random data. It sort of has high variance.
Any further questions? Yeah.
So for vector balancing, I'm wondering if
there are results that is not plus minus one, but unit complex numbers?
Ooh, I feel like the answer is probably, but I'm not remembering it off the top of my head, which is annoying. I have seen results like that on the way to getting things that were plus minus one, but yeah, no, there are definitely results in that format. If you ask me after lunch, I might remember one. Like it's slowly coming back, but I'm gonna have to dig through my iPad quite a ways to find it. Yeah, sure.
So just going back to the question of configurations of points, even just in the plane with like good discrepancy.
Yes.
I mean, you talked about sort of finding optimal configurations, but what do we know about the whole collection of low discrepancy? Like, can I sort of move from any one to any other, or is it kind of like an archipelago of like good?
Ooh, that's a good question. So can we move continuously from one good configuration to another? I don't know. I'm gonna guess probably if you move carefully. And they'll be pretty good. But I don't honestly know what the space looks like. I hadn't thought about that.
Okay, and any further questions? No. If not, let's thank Dan once more.